Right now, as you're watching this video, something is slowly destroying the metal objects all around you. It's eating away at your car, weakening the bridges you drive over, and turning your tools into crumbling orange powder. And the crazy thing is, you can't stop it. You can only slow it down. I'm talking about rust. And if you think rust is just some harmless orange coating that makes old things look weathered and vintage, you're in for a shock. Rust is one of the most destructive forces on the planet, costing the global economy over $2.5 trillion every year. That's roughly 3% of the entire world's GDP just vanishing because of this orange enemy. But here's what really blows my mind. Rust isn't some rare chemical reaction happening in extreme conditions. It's happening constantly, everywhere, all the time. That bike in your garage, rusting, the steel frame of the building you're in right now, slowly rusting. Even the Statue of Liberty, one of the most iconic monuments in the world, would have rusted away by now if it wasn't for some clever chemistry that accidentally saved it. So today, we're diving deep into the secret life of rust. We're going to explore what it really is, why it happens, and why this simple chemical reaction is one of the most expensive problems humanity has ever faced. Trust me, by the end of this video, you'll never look at that orange stain on your car the same way again. Let's start with the basics. What is rust? Here's the thing. Rust isn't actually a thing that attacks metal. Rust is metal. Or more specifically, it's what iron becomes when it reacts with oxygen and water. The scientific name for rust is iron oxide, and it forms through a process called oxidation. Now, you might be wondering, why does this even happen? Why can't iron just stay as iron? Well, here's where it gets interesting. Iron, in its pure metallic form, isn't actually the most stable version of itself. It's kind of like a wound-up spring, full of stored energy, just waiting to relax into a more stable state. And that stable state is iron oxide, also known as rust. Think of it this way. Imagine you're standing at the top of a hill. You could stand there forever, but if someone gives you a little push, you're naturally going to roll down to the bottom, right? That's basically what's happening with iron. The metallic form is at the top of the energy hill, and rust is at the bottom. Oxygen and water are the push that gets the process started. And speaking of curiosity and discovering how the world works, if you're the kind of person who loves understanding these everyday mysteries, you're going to love what we've put together for you. Check the description below to download our free ebook packed with 50 DIY science experiments and fascinating science facts. It's perfect for anyone who wants to explore the chemistry and physics happening all around us, including some cool experiments about oxidation and corrosion you can try at home. Seriously, grab it while you're thinking about it. Now, back to rust. The chemical reaction that creates rust is actually pretty simple on the surface, but what's happening at the atomic level is fascinating. When iron comes into contact with water and oxygen, a chemical dance begins. Water acts as a medium that allows electrons to move around, and oxygen is desperate to grab those electrons. Iron atoms start losing electrons to oxygen atoms, and this process creates iron ions. These iron ions then combine with oxygen to form iron oxide, which is rust. But here's the sneaky part. Once rust forms on the surface of iron, you might think it would create a protective barrier, right? Like a shield that keeps more oxygen and water from reaching the metal underneath. And for some metals, that's exactly what happens. Aluminium, for example, forms a thin oxide layer that actually protects it from further corrosion. That's why aluminium doesn't rust. But iron oxide, it's porous and flaky. It's like trying to use a sponge as a raincoat. Water and oxygen just seep right through it, reaching the fresh iron underneath and continuing the rusting process. And as the rust forms, it actually takes up more space than the original iron did, which causes it to flake off and expose even more fresh metal. It's a vicious cycle that feeds itself. And it gets worse. Rust doesn't just sit on the surface. It can penetrate deep into the metal, creating structural weakness. That's why a rusted beam in a bridge isn't just ugly, it's dangerous. The rust has actually compromised the integrity of the metal itself. Have you ever noticed how rust seems to spread faster in certain conditions? That's because the rate of oxidation depends on environmental factors. Salt water accelerates rusting dramatically, which is why cars in coastal areas or places that salt their roads in winter rust so much faster. The salt acts as an electrolyte, speeding up the electron transfer process. It's like adding fuel to a fire. Temperature matters too. Warmer temperatures generally speed up chemical reactions, so rust forms faster in hot, humid climates. And if you've got both heat and moisture together, like in a tropical environment near the ocean, you've basically created rust paradise. Now, here's an important distinction. Not all metals rust. In fact, only iron and alloys that contain iron, like steel, can form rust specifically. Other metals corrode, but they don't rust. Copper, for example, forms that beautiful green patina you see on old pennies or the Statue of Liberty. That's copper oxide and copper carbonate, not rust. Silver tarnishes, turning black from silver sulfide. Aluminium forms aluminium oxide, but none of these are rust. So why is iron so special? Or should I say, so vulnerable? It comes down to iron's position in the reactivity series of metals and its electron structure. Iron sits in this sweet spot where it's reactive enough to readily give up electrons, but not so reactive that it immediately reacts with everything like, say, sodium or potassium would. This makes iron useful for construction and tools because it's strong and relatively stable. But it also means that in the presence of oxygen and water, which are literally everywhere, it will slowly but surely corrode. Steel is mostly iron with a small amount of carbon and other elements added to make it stronger. But that doesn't protect it from rust. In fact, most steel is just as vulnerable to rusting as pure iron is. That's why steel cars rust, steel bridges rust, and steel buildings rust. Stainless steel is the exception. It contains chromium, which forms a protective oxide layer that actually does shield the metal underneath from oxygen and water. That's why your kitchen sink doesn't rust. But even stainless steel can corrode under certain extreme conditions. All right. Let's talk about the elephant in the room. How much damage is rust really causing? The numbers are staggering. As I mentioned earlier, rust and corrosion cost the global economy about $2.5 trillion annually. To put that in perspective, that's more than the entire GDP of France. Every single year, in the United States alone, corrosion costs are estimated at over $276 billion per year. That includes everything from maintaining infrastructure like bridges and pipelines, to replacing corroded parts in vehicles, to treating water systems damaged by corroded pipes. Think about your own life for a second. How many times have you had to replace a car part because of rust? Or throw away a tool because it had corroded beyond use? Or deal with rusty pipes in your home? Each of those is a small personal cost, but when you multiply it by billions of people and thousands of industries, it becomes this massive economic burden. Bridges are a perfect example. There are over 600,000 bridges in the United States, and a huge percentage of them are aging and dealing with corrosion. Some bridges have been closed or had weight restrictions placed on them specifically because rust has weakened their structural integrity. Fixing or replacing these bridges costs billions of dollars. The shipping industry loses massive amounts to rust. Ships are constantly exposed to salt water, which is like steroids for rust. Despite extensive anti-corrosion measures, ship hulls, propellers, and engine parts still corrode and need regular maintenance and replacement. And it's not just big infrastructure. Rust affects everything: your washing machine, your bicycle, your outdoor furniture, your barbecue grill. All of these things are slowly being eaten away by oxidation. But here's where it gets really interesting. Rust shows up in places you'd never expect, and sometimes with consequences that might surprise you. Take the Titanic, for example. Right now, over 2 miles below the ocean surface, the wreck of the Titanic is being consumed by rust. But it's not just regular rust. There are actually bacteria down there that feed on iron, accelerating the rusting process. These bacteria, called rusticles because they look like icicles made of rust, are quite literally eating the ship. Scientists estimate that the Titanic could completely disintegrate within the next few decades because of these rust-eating microbes. Or consider this: blood is red because of iron, hemoglobin. The protein in red blood cells that carries oxygen throughout your body contains iron atoms. Now, your body has sophisticated systems to prevent that iron from oxidizing the way it would outside your body. But in a sense, your body is constantly managing a controlled version of the same chemistry that creates rust. Pretty wild, right? Here's another one. Mars, the red planet, gets its distinctive rust-colored appearance from iron oxide. That's right, Mars is basically a giant rusty rock. Billions of years ago, Mars had water and oxygen in its atmosphere, and the iron in the Martian soil oxidized, covering the planet in rust. When you look at pictures of Mars, you're literally looking at a planet-sized example of the same process that's attacking your car. And did you know that rust can actually be magnetic? While iron itself is magnetic, and rust is made from iron, the magnetic properties change depending on the type of iron oxide. Some forms of rust are magnetic, others aren't. This is why a rusty nail might still stick to a magnet, but a heavily rusted one might not. So if rust is such a huge problem, what are we doing about it? Humans have been fighting rust for as long as we've been using iron, and we've developed some pretty clever strategies. The most obvious method is creating a physical barrier. Paint, for example, keeps oxygen and water away from the metal surface. As long as the paint remains intact, the metal underneath won't rust. That's why you see steel bridges and structures painted regularly. It's not just for aesthetics, it's essential maintenance. Galvanization is another technique. This involves coating iron or steel with a layer of zinc. Zinc is more reactive than iron, so it oxidizes first, sacrificing itself to protect the steel underneath. That's why galvanized steel, like the kind used in many outdoor structures and fences, lasts so much longer than regular steel. The zinc layer acts as both a barrier and a sacrificial anode. Chrome plating works similarly, creating a shiny, protective layer over steel. That's why chrome-plated car parts resist rust so well. Oil and grease create a water-repelling barrier, which is why you should oil your tools and bike chains regularly. No water means no rust, or at least much slower rust. Some modern approaches are even more sophisticated. Cathodic protection uses a small electrical current to prevent oxidation. You might not realize it, but this technology is used to protect underground pipelines, ship hulls, and even the steel reinforcement in concrete structures. There's also research into new alloys and coatings that resist corrosion better than traditional materials. Scientists are developing nano coatings and special polymer treatments that could revolutionize how we protect metal from rust. But here's the reality. We can slow rust down, we can delay it, we can make it much harder for rust to form, but we can't stop it completely. As long as iron is exposed to oxygen and moisture, even in tiny amounts, it will eventually rust. It's not a matter of if, but when. Now, you might be thinking, okay, rust is expensive and annoying, but why should I really care on a deeper level? Here's why. Rust represents something fundamental about our universe. It's a reminder that everything is constantly changing, constantly moving toward a more stable state. In physics and chemistry, this concept is related to entropy, the idea that systems naturally move from order to disorder. When we refine iron ore to create pure iron and steel, we're putting energy into the system to create that ordered, useful material. We're fighting against nature's preference for disorder, and rust is nature slowly reclaiming that energy, returning the iron to a more disordered, lower energy state. It's the same principle behind why buildings crumble, why mountains erode, and why everything around us is constantly wearing down. The universe favors disorder, and we're constantly fighting against that tendency to maintain the things we build and create. But here's the beautiful part. The fight against rust has driven innovation. It's pushed us to develop new materials, new technologies, and new understanding of chemistry and materials science. The billions of dollars we spend fighting corrosion have resulted in breakthroughs that benefit us in countless other ways. Stainless steel was invented specifically to address the rust problem. Now we use it for everything from medical instruments to architecture. The study of corrosion has led to advances in electrochemistry that benefit battery technology and renewable energy storage. In a weird way, rust has made us smarter. It's forced us to understand the world at an atomic level and to engineer solutions to natural processes. That's pretty remarkable when you think about it. So let's wrap this up. Rust isn't just some orange stain that makes things look old. It's a fundamental chemical process that's constantly occurring all around us, quietly destroying trillions of dollars worth of infrastructure and objects every single year. It's iron returning to its natural state, iron oxide, through oxidation. It's accelerated by water and salt, and it's nearly impossible to stop completely. Only iron and iron-containing alloys like steel can rust, though other metals corrode in their own ways. We've developed numerous strategies to fight rust, from simple paint and oil to sophisticated galvanization and cathodic protection. But ultimately, rust will always win in the long run. We can only delay the inevitable. The next time you see that orange coating on an old bike or a bridge beam, remember that you're witnessing one of the most destructive and expensive chemical reactions on Earth. You're watching atoms rearrange themselves, electrons moving around, and the universe's preference for disorder playing out in real time. And that's actually kind of beautiful in its own destructive way. If you enjoyed diving into the science behind everyday phenomena like rust, make sure to hit that subscribe button. We've got tons more videos exploring the hidden science all around you. Drop a comment below telling me what you'd like us to explain next, what everyday mystery keeps you up at night. And don't forget, check that description for our free ebook with 50 DIY science experiments. There's a whole world of chemistry, physics, and biology happening right under your nose, and once you start seeing it, you can't unsee it. Thanks for watching, and I'll see you in the next video. Stay curious.